Hey everybody, I was taking a look at the list of attendees. I know some of you out there on the interwebs, so good to sort of see you again virtually. And for those of you that I haven't met, hi, I'm Travis. I currently work as the technical lead for public sector at IBM Quantum. And when we think about quantum computing and quantum algorithms, I think there's been a lot of really exciting work that's come out of IBM, especially over the past few years, anchored in our vision for how the future of computing and kind of best-in-class computational capabilities, quantum or classical, can be brought to bear to solve the most pressing problems that face society today. So with that, I'll try and advance the slide. So one of the kind of anchor points that I want to use for our conversation today is that really the future of computing is heterogeneous. And there's a sense in which this has absolutely nothing to do with quantum computing. We witnessed the rise of projects like the Colossus by xAI. We witnessed, Stargate with OpenAI, et cetera. And the future of computing, we have this notion that, oh, well, we have to be building these different kinds of AI infrastructures. We have classical HPC that we can be brought to bear on the problem. And then somehow there's this thing called quantum computing that slides into the scene there. More seriously, though, the plethora and explosion of new kinds of compute hardware suggests that how we think about designing algorithms to solve pressing problems and to develop applications needs to change. And in particular, it means that we need to be thinking about how we take the best of what a given compute capability can do and how we bring those best-in-class capabilities together to solve interesting problems and to solve them in novel ways. And so with that, on the quantum side of things, because this is a quantum, the quantum talk, just want to give a little shout out to some stuff that we're planning to build here over the coming years. So what this is an artist rendition of a data center in Poughkeepsie, New York, which is about maybe an hour from where I'm sitting right now. In the upper right of the figure, we see 4 IBM Quantum System 2s. These are freestanding modular quantum computing systems, very large dilution refrigerators that we're using to explore building out large-scale quantum computing infrastructure. On the left-hand side, towards the rear of the graphic, we see a rendition of IBM Quantum Starling. This is the first fault-tolerant quantum computer. We plan to develop this and have this available for our customers and clients to use by 2029. Given our current thinking on the architecture and what we know about quantum error correcting codes, we envision that Starling will be about 200 logical qubits and capable of executing about 100 million operations. Then later in the mid-2030s, we have IBM Quantum Blue Jay, left-hand side of the screen, closer to the foreground. There, that we envision that being about 2,000 logical qubits and running about 1 billion quantum gates. These systems are not just simply artist renditions that are very beautiful. We have a roadmap. You can go Google that, IBM Quantum Roadmap 2025. We have a very credible plan of how we're going to de-risk the engineering of these large-scale quantum computing systems. And we remain fairly confident that we can achieve these milestones in the timeframes that we've set out. So we have this kind of hardware coming, and that's very exciting. And we have the kind of hardware that companies like IBM have put on the cloud today and that people can access through platforms like Qubit and et cetera, right? And so, when we think about developing new kinds of quantum algorithms to take advantage of this hardware, one of the things that we've really been excited about and working on for the past few years is how we can develop new quantum algorithms that are based on quantum and high performance computing. And we are really taking a very bold stance that the combination of those two compute capabilities in particular should allow us to unlock quantum advantage by 2026. We have some reasons for that we'll get into, technical reasons in a couple of slides. The essential point is to recognize that quantum computers are really good at generating samples from probability distributions and doing other kinds of computations. But we also have decades and decades and decades of research on how you use high-performance computing to solve interesting computational problems. And there's a whole community of researchers out there who, get up every day and they think about developing code for those systems. They think about developing new uses for those systems, et cetera. And so we want to partner with HPC providers in order to find new ways of developing quantum algorithms. And so shown on the bottom of this slide are just some examples of various papers around this notion that we've introduced called quantum-centric supercomputing. Now, Kenny sort of stole the thunder here, but that's okay, Kenny. So thank you for giving the shout out around this National Quantum Algorithm Center. So this is a partnership that we launched with the state of Illinois late last year to develop this algorithm center in the Illinois Quantum and Microelectronics Park and to really develop new applications and algorithms, both for scientific use, also commercial use, et cetera. And so we're really excited to see the work that will come out of this algorithm center in the coming years. Now, one of the reasons why we're very interested in quantum and HPC is we've already done our own work showing how using these quantum-centric supercomputing approaches, we can get comparable and to best-in-class classical methods results from a quantum computer using an amount of time that is actually fairly modest. In this case, maybe about 2 hours of quantum compute time, whereas using this self-same problem in a fault-tolerant way would take about 13 days, or if you did something like VQE, it might even take 3 million years. And so we're really excited to see how all of these algorithms can come together, how we can tackle new kinds of problems, etc. And so we'll just close. Anyway, I guess everyone has a platform. We have a platform too. Okay, it's based on the Qiskit SDK, the most popular developer kit. We have these Qiskit add-ons, which allow researchers to develop new capabilities and kind of tools that they can plug into their workflows. And we have Qiskit functions. Various companies like Q-Control, Kedma, Algorithmic, etc., that provide application level capabilities that can be scaled and that leverage the best in class of what our ecosystem has. So with that, I will give the QR code for the IBM Quantum Platform and say that if you want access to the most performant quantum computers, go scan that QR code. Thanks.